Okay. Good afternoon, everyone. I'm Cheng-En from National Taiwan University, and thanks for attending today. The subject of my presentation is a Lameness detection system by tracking leg key point of pigs and using CNN. And my advisor is Dr. Yan Foucault. This is my outline. And first, I'll let you get some introduction. As an island with a vibrant agricultural history, Taiwan holds a significant place in global pig farming. And this industry has an important influence on the economy, providing a steady supply of pork, which is a primary protein source in our dietary habits. And the pie chart illustrates the production value percentage of livestock in Taiwan. We can find pigs account for 41% in this category, and its value had reached $27 billion in 2022, which is the biggest part of Taiwan's livestock. But like any other husbandry, pig farming faces challenges. One of the major health issues that pig confronts is lameness, which is the condition of being unable to walk well because of the injury to the leg or foot. And lameness in pigs can dramatically impact their welfare and productivity. It causes suffering and stress in affected pigs, reducing their feed intakes, growth rates, and overall well-being. Consequently, it can decrease the financial return for farmers, having a profound effect for the entire industry. In the past, we relied on visual inspection and palpation, observing changes in pigs' walk and posture. And experienced farmers often notice subtle signs, like uneven walking or reluctance to move. Though insightful, this process is highly subjective and time-consuming, so potentially leading to misdiagnosis. Moreover, although the relatively objective pressure analysis method has been derived, its high cost and low popularity make it difficult to be considered as a feasible compromise to pursue better productivity. Developing more standardized, low-cost method is essential. So, here's my objective. And the ultimate target is to replace the pressure method in the pig industry. And let's talk about the method. This is my system pipeline, and I record pigs walking video, and then use SLEEP, the deep learning framework, and the Cheng-En deep learning key point tracking model. After that, I do the walking information analysis, and then compare to the pressure raw data. If the system doesn't work well, I will optimize my training process to get a better result. But if the system is good enough, it can be used to detect lameness in pigs precisely. For image acquisition, I record the videos of pig walking in a pig farm in Linkou district of New Taipei City in Taiwan. Steel wire fences on both sides of pigs' walking path are installed, ensuring consistency in the direction of pigs' movement. Since pigs move quickly through the fences, to avoid motion blur, I chose to record the video at a shutter speed of 1/800 seconds instead of 1/60 seconds. We can see frames captured with a 1/60 seconds shutter speed have some significant blur, like this and this. So, which is not desirable for model training. I use SLEEP as my deep learning framework. SLEEP stands for Social Leap Estimate Animal Poses. It is renowned for its method of tracking key points in animals. Notable not just for its precision and computational speed, but also for its highly adaptable deep learning model and the intuitive graphical user interface. I can say this system simplifies the task while ensuring high accuracy, making it a powerful tool for animal behavior analysis. The labeling process is finished in SLEEP. The pig foot can be divided into 4 parts, just like this picture. front right, front left, and back right and back left. And in the labeling process, I use the peaks hills, this part, as the uniform standard for annotation. Here's an example. My data set consists of 10 videos with about over 3,000 frames in total. And I labeled over 1,600 frames randomly picked by sleep. And there are 2 breeds of pigs in the data set, which are Landrace and Yorkshire. Image augmentation methods are implemented, which include horizontal flip, brightness, and contrast adjustment. Here are my training details. Okay, for the model's performance evaluation, object key point similarity, or OKS, is used. It measures the precision of predicted key points on an object, considering the object scale and key point similarity. It is more effective for real-world scenarios, especially in tracking with different size and poses. And OKS in MAP integrates OKS into MAP metric, commonly used in object detection, enhancing its relevance in model evaluation. By the way, I want to introduce the terminology of the evaluation. We can look at this picture. Swing. Swing refers to the interval between the heel taking off from the ground and the next time the same heel strikes the ground. And oppositely, stance means the interval that the heel keeps striking the ground. Overall, by adding these 2 processes in a working period, we can get strike, which is a period of 1 step. In my research, I want to focus on the stride length, stride time, and stance time of pigs. Finally, let's go to the result. The visibility precision of the model reached 95%, and OKS MAP for the model's performance achieved 0.53, and the average localization error is 9.6 pixels, which means the average difference between the system predicted locations and actual location is around 10 pixels. And the precision recall curve at every different OKS threshold is shown in this way. And the box plot depicts the error situation for each foot. Each foot. And we can get a clear understanding of the model's accuracy for individual foot. The probability distribution plots are shown. The left part is about the localization error distribution, and the right side is about object key point similarity. Here comes the analysis of the key points location result. The plot can be divided into 2 parts. The upper part depicts the x direction location of key points tracking, and the lower part means the y direction. Besides, the y-axis for each part is the image size respectively, is 1980 pixels and 1080 pixels. And the x-axis is the frames in the corresponding videos. So these plots help us to realize the location versus time of the tracking result. So we can see these points refer to the timing when the foot takes off, like this. And this point refers to the timing when the foot drops. With this information, we can calculate and get the average stride time and the average stance time accordingly. Next, the trace plot shows the spatial distribution of key points tracking. As the plot shows, the V-shaped place means the peak steps, and the lowest part of the V is the stepping point. Accordingly, we can calculate the stride length and of each step, and then finally acquire the average stride length. So, besides, I adopt the Lameness standard developed by the collaboration between a US company named Cheng-En and the Department of the Animal Science at the National Taiwan University. This standard, known as the asymmetry index, categorizes the severity of lameness into 3 levels: acceptable and normal, acceptable, and severe lameness. My research will utilize this standard for further comparison and analysis. These lameness standards are used to examine the following types: front foot divided by hind foot, and left foot divided by right foot, and stride length, stride time, stance time information were taken into these 2 types. Next, after we got the working information and the lameness standard, the accuracy of the comparison with pressure met data is crucial. High accuracy will effectively enhance the reliability of the method. Hence, I analyzed the result of these 2 methods. As a result, in the comparison, the mean absolute error of stride length, stride time, and stance time are 4.5%, 5.06%, and 11.28% respectively. Finally, if the above analysis and comparison are good enough, it becomes a reliable detection system, lameness detection system, which can precisely categorize each peak into different lameness levels and calculate its corresponding asymmetry index as well, making the users and farmers easily realize the condition of the peak's gate.
We are running out of time. Can you go to the conclusion directly?
To improve the video quality and the dynamic performance, I should set the camera's frame rate to 60 FPS or even higher to follow the motion recording parameter formula. To sum up, currently, I developed a foot key point tracking model for the lameness detection system and train a unit model for tracking leg key points that achieve 0.53 OKs MAP and the average localization error of 9.6 pixels. Most importantly, the similarity between the methods are there. And the pressure met analysis. Pressure met has achieved MAE of stride length, stride time, and stance time of 4.5, 5.06, and 11.28 respectively. Thanks for listening.
I think we have 1 minute for quick question, please. Yeah, please.
Thank you for the presentation. So I'm quite not familiar with the topic. I was wondering, because in the data you took, you make the peak come in the treadmill or something like that. So how long does it take for someone to detect the lameness, and how much time would you save by doing your method compared to someone detecting this in the real environment?
If the video are recorded completely, and the lameness result will be finished in almost because the result have to be processed by me, because I have to compare it to the pressure met. So if you want to get a accurate result, so you have to spend like 1 to 2 hours to get the lameness result.
My question is more like, someone go to the pork building, how long does it take for this person to detect?
To record a video?
No, if someone doesn't use this system.
For the expert,
for our expert.
to recognize them is a peak.
for the individual pigs, like expert spends like 1 minute to examine the Lameness. Yes.
Because we're running out of time, so you can exchange ideas later. So that's thanks, Ms. Zhang again.